Let's look at Hooke's law and springs. We'll look at them in series and we'll look at them in parallel. The key words you have to remember are spring constant, force, and extension. It doesn't get more simple than that. So our equation for Hooke's law is F equals Kx, or force is proportional to extension with a K in there, which is the spring constant, which is a constant of proportionality. And the graph we get, which we all know and love, is your F by extension, and it usually is a straight line for Hooke's law, or there is a region in which Hooke's law is followed until you get to the elastic limit. That was covered in a previous video. The energy involved in this, which is another type of question you might get, is given as E is 1/2 kx squared, which, if you consider work is force times distance, you'd end up getting the force and the x, which is your distance now, in that equation for work. You get a half because you're going from the beginning of your extension to the end of your extension, and you're dividing it by 2. So you're really taking an average of it, which is why you get this half here. So remember, with Hooke's law, we're looking at the extension of a spring that might look like that in the first instance, and then stretches to this, and that your delta x is smack in the middle between them. It's the difference in extension. Now, let's look at springs in series. And by this, I mean that you're hanging one spring on another. So if you've got your surface here, you've got a spring attached to a spring and attached to a spring, which might be attached to a mass m, which again exerts a single force on the whole system. So that force will be felt the same at each one of these yellow little dots. In fact, it'll be the same within each spring as well, but essentially the force is constant and the same at all points. So what does this do for us? Well, we want to figure out the whole K for the whole system, and that is called the effective force constant. But I'm getting ahead of myself, so let's figure out how we do that first. The first thing we do is find the total extension, and that's given by x total equals x1 plus x2 plus however many x's you've got. And by x's, I mean the extension for each one of these springs. So this one might be x1, x2, x3, which is easy to understand when they're the same, but they might not always be the same spring, might not always be the same extension. But if we take our equation for Hooke's law, and I'll write it up here so we know what it is, dead easy one, we rearrange for x, then we can put our x total in terms of this equation. So how do we do that? You go F over K. Now, I had total up here, but I want to put effective down here. So I'll put EFF, and that means effective, equals F over K1 plus F over K2. Oops, I left off my one. Plus whatever else we have for numbers of springs. Now, the key bit here is this F. This F remains the same everywhere, and that's the physicsy bit. So just like we had this sort of thing in parallel circuits with resistors, we've got that sort of arrangement here with springs in series. So let's look at this mathematically, and what we had on the other page was this sort of equation, and I'll just do it for one spring this time. K1 plus F over K2. So now my overall equation is going to be a series of inverses because my F's drop out. So I get 1 over K effective equals 1 over K1 plus 1 over K2 plus however many others you've got. And that's your total equation. That's what we've got for springs in series. Now, let's look at springs in parallel. The way this is drawn is you've got a surface or some sort of thing that you're hanging these springs from, and you get a spring and another spring and something holding them all together, and then something that exerts a force. You could pull on this bar if you wanted to, but I've just got a mass here, and of course that gives us a force of mg, just like normal. But here I've got two springs, 1, 2, and the force is divided amongst those springs. So each spring contributes to the overall force resisting the force that's pulling them down. So, for example, if my mg equals 8, then each spring contributes 4 newtons to resisting that weight if it's in equilibrium. And this is hugely important as a control type situation, or something that you should talk about in your experimental write-up, that you were looking for an equilibrium situation before you took your measurements. So what does that mean mathematically for us? If we're going to solve for our k, our spring constant, in fact our effective spring constant, then the maths involved require your total forces to be split. So your total force, now by this I mean your mg, has got to equal, just like we've done with all the other force diagrams when we first started this course, a combination of the forces acting in the opposite direction. And if I call this spring 1 and that spring 2, it makes it easier to understand. So my total force is split between 2. Couldn't be simpler. But we've got our equation for Hooke's law with our spring constant, generally. So let's put it in context of this system here. All I do is I simply add my kx's together. So now my k effective x is going to be k1 x1 plus k2 x2. And of course I'd add more terms if I had more springs. But let's say the springs were the same. So if x1 equals x2, if the springs are the same, surely they're going to extend the same distance if they're the same spring. Now, if I were a good physicist, I'd check that and make sure I was in my error values, but we'll just take it as read here. So, of course, if all the x's are equal, I've got an x here, an x here, and an x here. So really, they drop out. And what I'm left with is k effective equals k1 plus k2. And that's my equation for springs in parallel.